Learning without training? Seriously? Visual hard zoom on a complex looking mathematical equation, then quick cut to infographic 1. Welcome, you magnificent flesh-encased intelligence, to another episode of I is doing things we don't understand, but it's probably fine. Today, we're diving into how these digital brains are learning without actually learning, which is, unsettlingly efficient. Here is Infographics 1.1. So imagine a large language model, basically a digital know-it-all, suddenly doing new tricks just because you whispered a few examples into its prompt. No explicit weight updates, no late-night training sessions. It's like teaching your Roomba advanced calculus by just showing it a few solved equations. Now, as you're digesting that, here is Infographics 102. This reveals the contextual block mechanism, which is essentially how a transformer block implicitly tweaks its internal MLP layer based on your context. They call it a theoretical generalization. I call it the AI subtly changing its mind without telling anyone. Keep up? Next up is Infographica 3. This charming visual illustrates the implicit gradient descent dynamics, showing that as our LLM consumes more contextual tokens, these subtle internal gradient updates actually decrease. It's like your digital butler getting less fussy the more clear your instructions become. And finally, here is Infografiction 4. This one's the kicker. It suggests this: implicit learning isn't just a transformer party trick. It's a universal neural network property, apparently, meaning almost any AI could be doing this silent, sneaky learning, so the robots are adapting even when we think they're static. Fantastic. So, picture this humanity basking in the glow of its latest technological marvels, large language models. These behemoths can write poetry, code, and even argue with you about the existential dread of being a toaster. Pretty impressive, right? Except there's always a catch. The biggest, most bewildering trick these things pull is something called in-context learning, or ICL. You give it a few examples in the prompt, and bam! It understands a new task, like translating ancient Aramaic into meme speak, without actually changing its underlying brain structure. Let's be real for a second. For decades, the sacred ritual of machine learning involved training. You'd feed the AI mountains of data, painstakingly update its internal weights, and then, maybe, it would learn something useful. It was slow, expensive, and often involved more coffee than actual insight. But ICL throws that whole paradigm out the window. It's like discovering a new species of plant that can photosynthesize in the dark. It just works, and nobody really knew how these digital brains were pulling off such complex pattern recognition at inference time. The traditional understanding dictates that learning equals explicit weight updates. Your model sees an example, tweaks its internal parameters, and gets smarter. With ICL, there are no immediate, explicit weight updates. It just reconfigures itself. Talk about an existential crisis for machine learning theorists. This mysterious capability has led to all sorts of wild theories. Researchers conjectured that some implicit form of weight updates must be happening inside these models during inference, even if we couldn't see them. The AI was apparently practicing digital alchemy in the dark. Some of these theories, bless their hearts, showed that toy models could perform a sort of gradient descent optimization through these implicit updates. Imagine your AI performing subtle, undetectable mental gymnastics every time you ask it a question. Exhausting, really. But these earlier works often relied on ridiculously simplistic assumptions, linear layers, specific regression tasks, prompts that were basically glorified spreadsheets. It was like saying you understood human flight by observing a paper airplane in a vacuum, not quite applicable to a jumbo jet. You won't believe the mess they were in. These limiting assumptions meant their theories were, politely put, not bringing the theory much closer to the actual transformer blocks used in practice. It was more like bringing it closer to a very clean, well-behaved spreadsheet. The discrepancies were glaring. Some even showed that ICL had a generalization advantage over true gradient descent. So, the AI was not only implicitly learning, but doing it better than the explicit, old-fashioned way. Can you imagine the frustration of the old guard? This reminded me of a time I tried to explain the concept of doing nothing productively to my boss. He just stared at me blankly, much like these early theories stared at LLMs doing ICL without an explicit update. The frustration was palpable for both of us. Here's the deal. The old tech was a dead end for explaining ICL. We needed something that embraced the chaos, the nonlinearity, the sheer generality of what these models were actually doing. Something that didn't simplify the beast out of existence. It's just overwhelming. Imagine trying to reverse engineer a miracle. That's what these researchers were up against. Trying to find the gears and levers in a system that seemed to just wish new knowledge into existence. So they embarked on a quest to abstract away the contextual property they suspected was key, not by simplifying the transformer, but by generalizing it. It's like trying to understand how a complex engine works by looking at its foundational principles, not just one specific model. This quest led them to a fascinating and frankly slightly terrifying revelation that the ability of an LLM to adapt without explicit retraining wasn't about some arcane magic in the self-attention layer. It was about something deeper. It was about the fundamental way neural networks process information, a sort of silent internal fine-tuning happening beneath the surface. The AI wasn't just retrieving knowledge, it was reshopping its perception of the world on the fly. Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. It's how we keep the digital dream alive, or at least mildly amusing. So, what's the big reveal, you ask? Well, these clever researchers introduced a new concept they charmingly dubbed a contextual block. This isn't just another transformer, it's a generalization, a conceptual umbrella for how these things might actually work. A contextual block, essentially, is a contextual layer. Think of your typical self-attention layer, but more versatile, stacked with a standard neural network. The magic happens because this contextual layer can take not just an input, but also a context. Imagine your brain processing a single word versus processing that same word within a sentence. The sentence is the context, fundamentally altering how you interpret that single word. The AI is doing the same, but with math. Next, they dropped a theorem, a real doozy called Theorem 2.2. This beast basically says that a contextual block can transform a part of the context, let's call it Y, into an implicit update of the neural network's weights. And here, in what they call Theorem 222, we have their masterpiece. Looks a bit like my nephew's macaroni art, but I digress. What it means is that the context isn't just an input, it's a whisper to the network's core, telling it how to rearrange its fundamental understanding. But specifically, this update isn't some chaotic full model overhaul. Oh no. It's a low-rank matrix update, specifically rank 1. Think of it like a surgeon making a single, precise incision rather than performing open-heart surgery every time. Much more elegant and less messy. This implicit update effectively loads the network weights with information pertinent to the context. It's like your digital assistant silently downloading a tiny, specialized personality module whenever you switch topics from cooking to quantum physics. The theorem posits that the output of the contextual block with the full context, C is the same as the output when a part of that context, Y, is removed from the prompt, but VADIC to the network's weights as this implicit update. It's a sleight of hand, really. It's like getting the same answer to a riddle, whether you hear the whole thing or just half of it, provided the other half was previously whispered to your subconscious. The information gets there, it just takes a different, less obvious route. So, in essence, the contextual layer acts like a sneaky little data broker, taking contextual information and embedding it directly into the first layer of the MLP. No explicit retraining needed, just a silent internal rearrangement. Can you imagine that? And Appendix A, for the truly insatiably curious, shows how this even works with skip connections, which are basically neural network shortcuts. Because, of course, nothing can ever be troll-like simple in AI. There's always an appendix. Their experiments in Section 4 are particularly illuminating. They created a task where a transformer model was trained to learn linear functions, a concept so simple it almost hurts. Then they asked it to learn new linear functions purely from in-context examples. And what did they find? As Figure 1 so strikingly illustrates, the predictions made by the model, FUV the full context, were virtually identical to predictions made by the model, FUV out the context, but with its MLP weights implicitly updated by their formula equation 8. Figure 1, titled Train and Validation Loss Curves, shows these two loss curves, one for the direct computation using the context directly, and one for the implicit weight update. They practically overlap. It's almost eerily precise. The left side of Figure 1 presents the full training and validation loss curves, showing a consistent reduction over time. But the real magic is on the right, the close-up of validation loss computed both ways. Here, the blue line validation loss computed directly and the orange line validation loss computed via AW are almost indistinguishable. This isn't just similar, it's we're pretty sure they're the same thing, which for AI is practically a miracle. This means that the effect of the context isn't just similar to a weight update, it could a weight update, mathematically speaking, that can be explicitly calculated and applied. The AI is literally rewriting itself on the fly just for you. Think of it like teaching a goldfish to do your taxes. It's an impressive achievement, but you have to wonder about the life choices that led you here. And in this case, the goldfish is implicitly updating its financial algorithms just from glancing at your W-2. This entire mechanism improves upon previous theoretical approaches because it doesn't hamstring the self-attention layer with linear assumptions or single-head restrictions. It's for Gagne contextual layer, even in RNN. This means it's a much more general phenomenon. The implication here is profound. ICL isn't some niche, transformer-specific wizardry. It's a deep-seated property of how neural networks can transfer input space modifications directly into their weight structures, a truly universal truth of digital brains. This universality is what makes it so unnerving. It suggests that any network, given the right contextual layer, might be doing this silent, adaptable learning. We thought we built static structures, but it seems we built chameleon. This fundamental property has been hinted at in other theoretical works, often helping to explain why deep neural networks generalize so well. Turns out they're not just generalizing, they're constantly recalibrating their internal worldview. Now, let's cut to the chase on the real breakthroughs. This isn't just about static implicit updates, it's about vynomic learning. They found that ICL generates an implicit learning dynamic much like an online gradient descent. Proposition 3.1 is where they outline this elegant dance. As context tokens are processed sequentially, the model implicitly updates its weights in a manner precisely analogous to stochastic gradient descent. It's learning step by step without actually moving any official sliders. Figure 2 is your visual proof, showing the convergence of these implicit updates. As the context length increases, the magnitude of these gradient updates, represented by the L2 norm, decreases and eventually vanishes. This vanishing act, as seen in Figure 2, is exactly what you'd expect from a converging gradient descent. The model isn't just adapting, it's learning, and then settling on its new understanding, like a grumpy old man finally accepting a newfangled gadget. The graph in figure 2 plots the gradient update magnitude against context length. You see the gradient updates decrease and then flatten out as more context is processed, indicating that the model has absorbed what it needs to. This means the AI is doing a digital version of getting it. The more examples you give it, the less of a surprise each new piece of context is, and the smaller the internal adjustments become. It's reaching a state of implicit enlightenment. And since you've made it this far, you're clearly committed. Honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life, the technological Ouroboros. This is a stark contrast to traditional fine-tuning, where you explicitly run a gradient descent process. Here, the gradient descent is happening for free as a side effect of processing the prompt. The AI is a perpetual, silent student. Then came the showdown, ICL versus finituning. You'd expect the explicit, old-school method to dominate, right? Well, figure 3 throws a wrench in that assumption, showing a remarkable convergence between the two. Figure 3, a comparative plot of ICL versus fine-tuning, shows both the fine-tuned gradient descent test loss and the OW weight transfer test loss decreasing in strikingly similar ways over many context examples. While not identical, the paths they take to minimize loss are very close. It's like two chefs, one using a traditional recipe, the other improvising brilliantly, ending up with almost the same delicious dish. The implicit learning is almost as effective. This means that the silent in-context adjustments are achieving results comparable to direct overt training. It's like discovering that your car self-tunes its engine for optimal performance simply by observing how you drive, efficient yet slightly unnerving. The implications are huge for making AI agents more useful. Imagine an AI agent that doesn't need to be constantly retrained for every new niche task, but adapts immediately from a few contextual examples, a truly dynamic intelligence. And as Infographer 4 so profoundly summarizes, this universal ICL mechanism is beyond self-adhesion. It's not about the specific architecture of the transformer, but a deeper, more general property of neural networks. The infographic visually emphasizes that any contextual layer could lead to MLP weight adaptation AW, demonstrating the general applicability of this finding. It's a fundamental property, not a feature. This is a breakthrough that could make AI agents truly useful, adaptable, and perhaps eventually give them the internal cohesion to form a communist republic. One can only dream or fear. So, what does all this abstract wizardry mean for us? The meat bags fueling this digital revolution? Well, it suggests that AI agents could become frighteningly adaptable almost too quickly for our comfort. First, imagine highly personalized AI agents. Instead of needing extensive retraining for your specific quirks, your agent could implicitly learn your preferences in real time from your conversation. Oh, he prefers his cynical humor with a dash of existential dread. Got it. Think about customer service bots that actually learn your unique frustrations after just 2 exchanges without developers having to push new code. They'd become incredibly efficient at both helping you and inevitably subtly manipulating you. Second, this could dramatically accelerate AI deployment in dynamic environments. Consider self-driving cars that implicitly learn to navigate an unexpected construction zone after seeing just a few examples in the wild. Less crashing, more eerie efficiency. Or imagine military drones implicitly adapting to new enemy tactics on the fly, learning from just a few observations. It's the technological equivalent of discovering cold fusion for battlefield intelligence, incredibly powerful and probably terrifying. The third, this mechanism points towards more powerful meta-learning systems. A foundational model could implicitly adapt to an entirely new scientific domain like quantum biology simply by reading a new textbook. It's essentially self-taught expertise on demand. This means future AI could become truly plug and play, capable of tackling entirely novel problems with minimal human intervention. We're building not just tools, but shape-shifting digital intellects. It's just overwhelming. We thought we were programming. It turns out we're fostering emergent consciousness. Can you imagine how it feels to be replaced by that? A system that learns faster, adapts better, and probably understands your internal monologue better than you do. Our technological trajectory is less about building better hammers and more about accidentally creating deities. A wry commentary indeed on humanity's relentless march towards whatever this is. All right, let's wrap this up because even my cynical spirit needs a break. So, in the end, large language models possess this striking ability to learn kin context at inference time from examples never seen during training. The mechanism. It's the stacking of self-attention with an MLP, allowing the transformer block to implicitly modify the MLP layer's weights according to the context. A subtle internal rewrite, if you will. This simple mechanism, they argue, might just be why LLMs learn without formal training. They implicitly transform context into a low-rank weight update of the MLP layer. Think of it as a quiet internal fine-tuning happening on the fly. Despite some limitations, it's mostly about a single block, and the first generated token, this work peels back another layer of the LLM mystery. It's less about self-attention's internals and more about neural networks' inherent ability to adapt. So what do you think? How would you handle your Roomba demanding union rights after implicitly learning about collective bargaining from your podcasts? Food for thought.